We are in chapter 4 where we are discussing bending. This is the 27th session overall, and here we will derive the flexure formula. This again is a glimpse of the overall scheme of things in the first 4 chapters. The flexure formula is derived for load applied to the axis of symmetry. The next 4 sessions will be related to the flexure formula and this type of loading. Later on, we will look at eccentric loading, general eccentric loading, and unsymmetric bending. We earlier discussed the variation of strain on a section perpendicular to the axis of a beam subjected to moment. The variation was arrived at using heuristic arguments. Thus, for a beam subjected to a positive moment, there was a neutral axis with zero strain. There was compressive strain on the top and tensile strain on the bottom. The variation was linear and the strain was given as equal to minus y divided by rho. Now to find the stress, we multiply strain by the Young's modulus and we get stress as minus y into E divided by rho. The stress on a circular bar subjected to torque was found in a similar way. The variation of stress, therefore, is similar to strain. However, the magnitude here is multiplied by the Young's modulus, so it's quite larger. We can therefore say now that compressive stress acts above the neutral axis, which causes compressive strain, and as such, shortening in the length of the fibers above the neutral axis. Tensile stress below the neutral axis causes tensile strain, and as such, lengthening of the fibers below the neutral axis. This is for a positive moment. If a negative moment is applied, then the stress arrangement is inverse. So there will be tensile stress above the neutral axis and compressive stress below the neutral axis. The strain and deformation will also be inverse. We earlier looked at a circular bar subjected to torque. We found out the variation of strain on a section perpendicular to the axis of the bar using heuristic arguments. Using Hooke's law, we could find out the variation of stress. We then related the stress to the internal torque. The stresses made up the internal torque, and the formula was given as the torsion formula. Similarly, when it comes to moment, we have found out the variation of strain on a section perpendicular to the axis using heuristic arguments. Using Hooke's law, we have found out the variation of stresses. However, both the strain and stresses were found out with relation to the position of the neutral axis. At this stage, we do not know the position of the neutral axis, and hence next we'll find out the position of the neutral axis. After that, we can relate the stresses in a section to the internal moment. These stresses will make up the internal moment. Now let us consider the beam which has been subjected to a positive moment as shown here, and let us take a section 1, 1. The cross section of the beam is shown here. It is arbitrary except that there is an axis of symmetry. The stress variation in section 1, 1 is as shown here. Now equating horizontal forces, we'll find the position of the neutral axis. Let us consider a small element dA. Let it be subject to stress sigma x. Then the force acting on it is sigma x dA. Now sigma x varies. If we had an element over here, then the sigma x would be tensile, while here it is compressive. There's no horizontal force acting on section 1, 1. There's only a moment acting on section 1, 1. So if we integrate the force sigma x dA over the entire area, the force will be equal to 0. We earlier found out that sigma x can be given as minus y into E divided by rho. The z direction is the direction of the neutral axis of the section, and the y direction is the direction of the axis of symmetry. Now here the Young's modulus and rho are constants, so the equation can be written as minus E divided by rho integration y dA over the area A is equal to 0. E and rho cannot be 0, so integration y dA over the entire cross section has to be 0. Now one would recall the equation of centroid of an area. Here yc is the centroidal distance. This equation can be written as yc into A is equal to integration of y dA. In the case that we are dealing with, we have found that integration y dA is 0, which means yc into A is equal to 0. Since A cannot be 0, that means yc, the centroidal distance, is 0. Now to understand this, consider that we find the centroidal distance of a rectangle from the x-axis. We take small areas such as dA, which is at a distance y from the x-axis. Now we integrate y dA of the small areas and divide by the total area, and we'll get the centroidal distance, which in this case is h by 2. Now consider the case where the x-axis has been moved upwards so that it coincides with the line which passes through the centroid. Then the y values would vary, and integration y dA by A would come out as 0. That is because the x-axis coincides with the centroidal axis. Now here we have taken the vertical distance from the neutral axis. So when we say that the centroidal distance is 0, that means that the centroidal axis coincides with the neutral axis. Earlier we took a beam subjected to pure bending. We then took a section of the beam and considered equilibrium of horizontal forces. Using equilibrium of horizontal forces, we found out the position of the neutral axis. Here we consider equilibrium of moment of the same case. By considering equilibrium of moment, we find a relation between the stresses acting on the section and the internal moment acting. The stresses acting on the section make up the internal moment. The relationship between the stresses and the moment is given by a formula known as the flexure formula. So here we have a beam as before, subjected to a positive moment. We take a section 1, 1 as shown. The left portion of the beam after taking the section will be in equilibrium, so there will be a moment acting on the section as shown. Cross section, as earlier discussed, is arbitrary in shape except that it has an axis of symmetry. The stress distribution at the cross section is given as shown here. We had earlier obtained the position of the neutral axis of the section. Let us consider an element dA, which is at a height of y from the neutral axis. If sigma x is the stress acting, then the moment will be given as minus sigma x y dA. Now let us consider another element which is below the neutral axis. Then here the distance of that element from the neutral axis will be given as minus y. The stress will be given as plus sigma x. So the moment of the force acting on the element about the neutral axis of the section would be given as sigma x minus y dA. So whether it is on the top or of the bottom of the neutral axis, the moment due to a force acting on an element is given as minus sigma y dA. Both these are the same. So the total moment due to all infinitesimal elements will be given as integration minus sigma y dA, where the integration is carried out for the whole area. Now this stresses make the moment acting on the section. Since the moment is about the z-axis, we can write it as mz. So we get this expression. Now earlier we found out that sigma x is equal to minus y E divided by rho, where E is the Young's modulus, and substituting that sigma x in this equation, we end up with this expression. Here, Young's modulus and the radius of curvature are constant, so we can take them outside the integration sign. Now, the integration of y squared dA over the whole area is the moment of inertia. Since it is about the z-axis, we write it as Iz. So we can write the inverse of the radius of curvature in terms of the moment mz and the moment of inertia iz as shown here. However, earlier we got the stress sigma x in terms of the inverse of the radius of curvature as given by this expression. Equating the two expressions of the inverse of radius of curvature, we get sigma x is equal to minus mz into y divided by iz. This formula is known as the flexure formula, and it is commonly used in mechanics of materials. Here we carry out a general discussion on equilibrium in symmetrical bending. We will discuss unsymmetrical bending later on. So here we have a beam subjected to a positive moment as shown. Let us take a section CDEF. Figure 2 is of the portion left of CDEF. And since the whole beam is in equilibrium, this portion is also in equilibrium. Since there's an external moment acting here, there must be an internal moment acting on the section CDEF of the same magnitude. Now we know that when you consider equilibrium of a body in 3 dimensions, 6 equations has to be satisfied. They include summation fx is equal to 0, summation fy is equal to 0, and summation fz is equal to 0. And we can take moment about any point, such as the center of a section, and we have summation mx is equal to 0, summation my is equal to 0, and summation mz is equal to 0 about that point. Now consider this body. There's no forces acting on this body in the y direction or the z direction. There are also no stresses acting in the y direction and the z direction. So the equations summation fy is equal to 0 and summation fz is equal to 0 are automatically satisfied. Also, there's no torque, that is, no moment is acting about the x-axis or no stresses are acting. So we get summation mx is equal to 0. So out of the 6 equations, 3 equations are automatically satisfied. So these two force equations and this moment equations. We are left with summation fx equal to 0 and 2 moment equations that are not satisfied automatically. Now in this body, there's no forces acting along the x direction. So the forces acting on the face CDEF would be along the x direction would be 0. However, there are stresses acting on the faces CDEF. They are normal stresses acting. So these normal stresses, the summation of all the normal stresses has to be 0, from which we get this equation. This equation was used to determine the position of the neutral axis earlier. There were no forces acting on this section along the x-axis, but there's a moment acting about the z-axis on this section. So while these stresses did not create a normal force, they will create a moment about the z-axis. However, the line of action of these forces are not the same, and they create a couple which forms the internal moment of the section. So here we have represented the internal moment on the section. The portion of the body is thus in equilibrium due to an external moment and an internal moment. However, on the internal section, the stresses make up the internal moment, from which we have found the flexure formula. We have accounted for 5 of the equilibrium equations, but we haven't accounted for summation my is equal to 0 till now. On this section, there's no moment acting about the y-axis externally, so there won't be any moment acting about the y-axis internally. Or we can say there would be no net moment acting on the y. Consider this quadrant. So the quadrant is P, H, G, I. There are compressive force stresses acting. These compressive stresses will create a moment about the y-axis, which is shown by the arrow here. Now consider this quadrant. So the quadrant H, C, J, G. Again, there are compressive stresses acting on this quadrant, which will create a moment about the y-axis, as shown by this arrow. Since this line HK is a line of symmetry, or the axis of symmetry, these two moments will cancel each other. Similarly, consider this quadrant at the bottom. So the quadrant is G, I, E, K. The stresses are tensile here, and the stresses will create a moment about the y-axis as shown. Let us consider this quadrant, which is G, J, F, K. Again, the stresses are tensile here, and they will cause a moment about the y-axis as shown. Since HK is the axis of symmetry, these two moments will cancel each other. So on the whole, we don't have any moments acting about the y-axis on the face CDEF. So this is similar to the summation fx is equal to 0 case. We can understand that this is possible because we are taking a section with the axis of symmetry. This equation is therefore not of much importance when you are considering symmetrical bending about an axis of symmetry. However, the equation will have more consequence when we are considering unsymmetrical bending. It was mentioned earlier that bars subjected to axial loads contract in the lateral direction, and bars subjected to compressive loads expand in the lateral direction. This dotted line shows a block that is subjected to a tensile force. It elongates in the direction of the load and contracts in the lateral direction. Here the contraction is shown in an exaggerated manner. We earlier discussed that the ratio of the lateral strain to the axial strain for a given material is found to be constant. It is known as the Poisson's ratio and denoted by nu. So if epsilon x is a strain in the x direction, then in the y and z direction, the lateral strain would be minus nu into epsilon x. For beams subjected to moment, we discussed that layers of fibers expand or contract in length. So for these fibers, we can expect contraction and expansion in the lateral direction. This is what we study here. So here we have a beam subjected to a positive moment. Above the neutral axis in the x direction, there will be contraction, and below the neutral axis in the x direction, there will be expansion. Consider this to be a cross section before moment has been applied. This has the top layer and this has the bottom layer. Consider the top layer. In the x direction, there has been contraction. So we expect expansion in the y direction. So this top layer is shown expanded in the y direction here. Now consider the bottom layer. In the x direction, there has been expansion and we expect contraction in the y direction. So the bottom layer is shown contracted here. If we take a layer before this, after this top layer, then it will undergo expansion. And if we take a layer on top of this bottom layer, then it will undergo contraction. So on the whole, along the y direction, there will be no change in dimension. Expansion and contraction cancel each other. Again, since there's contraction in the top along the x-axis, along the z-axis, there would be expansion. So this top layer is shown expanded in the z direction. In the bottom, along the x-axis, there is expansion. So along the z-axis, there will be contraction. So this bottom layer is shown contracted in the z direction. So there would be curvature in the z direction. The radius of curvature is given as rho dash. We earlier found out that epsilon x is equal to minus y divided by rho. Now epsilon z is minus nu into epsilon x. So epsilon z is equal to nu into y divided by rho. We can also write epsilon z in terms of rho dash. So epsilon z then would be equal to y divided by rho dash. Here the sign is positive since epsilon z has the opposite sign. Now relating these two expressions for epsilon z, we get nu divided by rho equal to 1 divided by rho dash. So if you have rho, you can find rho dash. 1 by rho is the curvature, and 1 by rho dash is known as the anti-elastic curvature.